You may have noticed in the last video that when a function switched from increasing to decreasing or decreasing to increasing, that it happened at the top of a peak of the graph or the bottom of a valley. Okay, it's going to be important for us to determine where these peaks and valleys occur. So sometimes we're able to do this, that we're able to determine the largest y value using pre-calculus. Okay, for example, if we had a parabola, if it wasn't in the right form, we could complete the square to find its vertex, which would be the maximum or the minimum. Okay, this is the idea. We call these maximum and minimums relative extrema. So we're going to define that in this video and figure out how to use calculus to find them for more complicated functions, and in fact for the parabola as well. It's much faster using calculus. So let's let C be a number in the domain for the function f. Then we say, then we say that f of c, the y value, so maybe I want to emphasize that. So this is the y value at c, is a relative maximum or local maximum. Okay, these are sort of equivalent ways to say it. For f, if there is an interval, let's say a, b, that contains c, where f of x is less than or equal to f of c for all x in the interval. Okay, so what this says is that i.e., okay, f of c is the largest y value. Okay, similarly, f of c is a relative minimum if there is an interval a, b that contains c, where f of c is actually the smallest. Okay, so f of x is always bigger than or equal to f of c for all x in a, b. And then we say that the function has a relative extremum or local extremum if it has a relative max or min there. So we say extremum or extremum if we don't know if it's a max or min. Okay, just to say that it is some extreme value, but we haven't determined which one yet. And for the plural for extremum is extrema. Okay, so that's why this section is called relative extrema. So we're talking about plurals. Now, if C is the endpoint of the domain of f, then we only consider a half interval. So it doesn't need to be that C is in the middle of the interval or in between A and B. We might consider the interval from C to B, okay, depending on which, or A to C, depending on which endpoint it is for the domain of F. Okay, now intuitively, I sort of started to write this up above, but intuitively we say a y value, okay, I want to emphasize that. So a y value is a relative maximum if it is the largest y value in its neighborhood. So that, I mean, nearby to it. So in that sort of small, it could be a small neighborhood, okay? So in a small area surrounding it, it's the biggest y value. And it's a relative minimum if it is the smallest y value in its neighborhood. Okay, so let's look at an example with a graph. So we want to identify the relative extrema and classify it as a relative max or a relative min. so the domain here, we can tell there is points for every x value as long as we're bigger than or equal to -7. So the domain goes from -7 to infinity. Okay, so now we want to think about where we would have a relative maximum. Okay, so it looks like at x equals -4 that this point is going to be the biggest y value in a neighborhood that surrounds -4, right? It's the biggest in its sort of region. So we would say y equals 7 is a relative maximum, which occurs at x equals -4. Okay, so that's one relative maximum. It also looks like at x equals 5 that we have a relative maximum at y equals 4. Okay, so remember the y values are what the maximums are. Okay, the x values are just where they occur. Okay, now relative minimums. So at x equals 2, it looks like that y equals 0 is a relative min because it's the smallest y value in its neighborhood. Similarly, y equals 1 at x equals 7 is also a relative minimum because it's the smallest, it's the bottom of this valley. And also this endpoint. Okay, so the endpoint of the domain, y equals 3, this is also a relative minimum because it's at the end, so we only consider the half interval. So from -7 to somewhere outside of 7, in fact, you can go all the way to -4 if you want. This is the smallest y value. Okay, so this one is an endpoint. Okay, now there's one special point that's illustrated here at -1. Is this a max or a min? Well, on one side, so it's not an endpoint, right? And on one side, the values are bigger, whereas on the other side of it, the values are smaller. Okay, so this point is actually neither. Because it's not an endpoint of the domain, it has to be that it's the biggest or the smallest surrounding it. So we can't use a half interval. So you need to take some points on either side of it. And if we do that, then some of them are positive, some of them are bigger, and some of them are smaller. Okay, so that means it's not a minimum or a maximum. Now, what do you notice about all these extrema? So if we think about it, I want a different color here. So the derivative at this point is 0. The derivative at 7 is 0. The derivative at 5 does not exist. Similarly, at 2, the derivative does not exist. Okay, at -1, sorry, the derivative also is 0. Okay, but that was not a min or a max. So what happens, so if we look at all of these, the endpoint one is a bit special, okay, but all the other ones, the derivative is either 0 or does not exist. So that means that they occur at critical numbers. Okay, so other than the endpoint, all the relative extrema occurred at critical numbers in the graph. Okay, so this is actually always happens. So if you have a function f, it has a relative extremum at x equals c, then x equals c is a critical number or x equals c is an endpoint. Okay, so either if you have an extremum, it has to occur at a critical number or at an endpoint. Those are the only options. Now I want to point out, okay, so be careful. X is a critical number. Does not imply that there is an extrema. At x equals c. So you want to be careful. So for instance, at x equals -1 in this graph, it was a critical number, but it was not a relative extremum. Okay, so it goes the other way. If you have an extremum, it has to be at a critical number or an endpoint. If you have a critical number, it does not have to be an extremum. Okay, so now what we want to think is, well, how do we find these if we don't have the graph of the function? Okay, so let's think about what happened. So I'm going to think about the increasing and decreasing nature. So if we were to do our table that we've done in the past videos for increasing and decreasing, we would split our domain at each of these critical numbers. Okay, so that means that my number line, okay, would go from -7. I would split at -4, and then again at -1, at 2, at 5, and again at 7. Okay, now if we think about in each interval, okay, and from -7 to -4, our graph was increasing, and then it decreases until -1, and then it decreases again until 2, and then it increases, and then it decreases, and then it increases again. Okay, now notice, where did we get the extremum? So at -4, so okay, at 7 we had a min at the endpoint. At -4 we had a max. At -1 we had none. At 2 we had a min. At 5 we had a max, and at 7 we had a min. Okay, that's what we saw. So notice that when we got a maximum, as we go from the left to the right, the function increased and then decreased, right, at -4 and at 5. If we got a minimum, the function decreased and then increased, decreased and then increased every time we got a minimum, except the endpoint. The endpoint's a little bit different. So we can summarize this. Okay, so relative max switch from increase to decrease. Okay, relative mins switch from decrease to increase. Again, we're going from the left to the right. Okay, and we got no extrema or extremum if no switch. This is the idea behind the, I guess I should have written that down here, but this is the idea behind the first derivative test. Okay, so that's where I'm going to go now, and then we're going to do one example. So what does the first derivative test say? This is testing for extrema. So if c is a critical number, okay, for a function f, and we have c surrounded in some interval, okay, where f is continuous on that interval and differentiable on that interval, except maybe at c, C has to be the only critical number in that interval. Then we would say that f of c, so the y value, is a relative maximum of f if the derivative f prime of x is positive on the interval from a to c, so to the left of c, and negative on the interval from c to b. Okay, so in your table, you'd have c would be where you split, and it would be positive, so increasing, and then negative, so decreasing. Okay, and then you can see, this is why I do the arrows, you can see that you're getting a peak there. Okay, so that's why we get a maximum. Okay, it would say it's a relative minimum if the opposite happens. So the derivative f prime of x is negative on a to c and positive on c to b. Okay, so in your table, again, c is the only critical number, so in this area. Okay, so on the left of c, it's negative, okay, so it's decreasing. And on the right, it's positive, so it's increasing. And then you can see that you get a valley, right? So then at c has to be the smallest point of that valley. Okay, so that's the idea behind the first derivative test. Now let's just do an example. So find and classify all relative extrema for this function. So x cubed plus 3x squared minus 9x plus 4. So let's first note that the domain goes from negative infinity to infinity because it's a polynomial. So there's no endpoints, so we don't have to worry about that. So that means that all extrema will be at critical numbers. So we want to find the critical numbers. How do we do that? Take the derivative, set it equal to 0. So same thing we were doing before. So the derivative is 3x squared plus 6x minus 9, which if I simplify this, I can factor out a 3. So it's 3 times x squared plus 2x minus 3, which is going to be 3 times x plus 3 times x minus 1 in the factored form. Okay, so then I want to set the derivative equal to 0, because remember I'm trying to find my critical numbers. So that's when 3x plus 3x minus 1 equals 0, which means I have 3 things that are multiplied together equaling 0. One of them has to be 0. This one obviously cannot be 0 because it's 3. So it means one of those two is 0. So x plus 3 is 0, or x minus 1 is 0, which means that x equals negative 3 or x equals 1. So these are both going to be critical numbers for our graph, for our function. Okay, now I also want to see where the derivative is undefined, because I might get critical numbers from that. Although f prime is a polynomial. Okay, so there's no critical numbers of this type. I'm just going to write none. So these two are our only critical numbers. Okay, now we're just going to test for increasing, decreasing. So do our table, and then we just have to add one more step after to see whether or not these critical numbers are in fact relative extrema. So I'm going to split at negative 3 and at 1. Okay, these are places where the derivative could change. So I want to test something less than negative 3, maybe negative 4. Okay, so f prime of negative 4 is 3 times negative 4 plus 3 times negative 4 minus 1. Now, without actually computing this, this is a positive number times a negative number times a negative number. So I have two negatives multiplied together. That's going to give me a positive. And timesing by a positive is going to give me a positive. Okay, so I know that this derivative here is going to be positive. If I plug in something between negative 3 and 1, maybe 0, okay, f prime of 0 is going to be 3, 0 plus 3 times 0 minus 1. So here I have a positive times a negative. So one negative means that I'm going to get a negative at the end. Something bigger than 1, maybe 2. F prime of 2 is going to be 3 times 2 plus 3 times 2 minus 1. So here I have a positive times a positive times a positive. So I'm going to get a positive. Okay, so then I know that I am increasing because the derivative is positive on the interval from negative infinity to negative 3. From negative 3 to 1, I'm going to be decreasing because my derivative is negative. And then I'm going to be increasing after that. So, using the first derivative test, I can say that at negative 3, I'm going to have a relative maximum. Okay, and at 1, I'm going to have a relative minimum. Okay, so I want to find what these are. Okay, so that means I want the y values. Okay, so f of negative 3, so the y value at negative 3 is negative 3 cubed plus 3 times negative 3 squared minus 9 times negative 3 plus 4. So if you compute that, I think you get 31. Okay, this is a relative maximum for f. And f of 1, which I'm just going to tell you is negative 1, is a relative minimum of f. And those are the only extrema values.